Owl wings are incredibly advanced, and to give you an idea about just how many features they have on them, over the past year, we've done a few podcasts on different features of them, but would you believe that we still haven't covered all of them? For example, it is quite well known that owls have a serrated trailing edge, and that these serrations are there largely to reduce the noise. But did you know that they also have serrations on the leading edge as well? And these serrations are very different, and we'll see their effects are also very different as well. So in figure 1 in this paper, which we'll get to in a second, we see where these leading edge serrations occur and that they are very different to the trailing edge serrations. You can see the trailing edge serrations right here. They're very macroscopic and quite undulating, like they're quite smooth in the undulations, they're not very sharp. But unlike the trailing edge serrations that form along almost the entire leading edge, these leading edge serrations here form over the outer third of the leading edge. And what's more, these leading edge serrations are tiny compared to the trailing edge serrations, and the trailing edge serrations can easily be seen by the naked eye. They're very macroscopic, but the leading edge serrations are much finer and you need to zoom in a lot just to see them. Also, they are a lot more like tiny teeth that are jutting out, and they're quite sharp. And things get even stranger because apparently owls can generally be grouped into day-dwelling birds and nocturnal birds. And you might be thinking, okay, so what? They have different sleeping patterns, big deal. But in reality, this difference in sleeping pattern is very important because the nocturnal owls are far more stealth-oriented, and hence their wings have evolved to be quieter. So many of the flow control devices we see on nocturnal owls aren't found on daytime owls. That's insane. And coming back to these leading edge serrations, the question arises as to how they affect the owl's wings aerodynamics, if at all. Maybe they're just there for aeroacoustics, maybe they're there for aerodynamics. We'll need to find out. And to find out, we're looking at this paper called The Role of Leading Edge Serrations in Controlling the Flow Over Owls' Wings. And the great thing about this paper is that they tested a replica owl wing. So the wing was an exact copy of a real owl wing, and we see in figure 1b, the 3D printed model here. But one thing to note is that the wing was scaled down to 50% so it could fit into the water channel actually, and have a blockage ratio of 2.5%, which means that there's no correction factors required, and hence their experimental results are far more accurate. So remember how I said that these leading edge serrations were tiny? Well, here the authors say that they were about 2 millimeters in length, which is just about 0.018% of the chord. They also had a width of 1 millimeter, I guess the wavelength. So the amplitude was 2 millimeters, the wavelength was 1 millimeter. And they tested these wings with and without leading edge serrations with PIV, so particle image velocimetry. So the results give a lot of details about the velocities over the wing, and in figure 2, we see their water channel setup. Now, you might be wondering if you can test the wing, which usually operates in air, in water. And the answer is yes, you actually can, but with a couple important points. So generally air and water act the same way. So something that is aerodynamic will usually be hydrodynamic as well, and vice versa. That means that you can test an air-based object in water and a water-based object in air. But the two things you really need to keep watch on is cavitation and waves. So cavitation is when you create these tiny bubbles of really low pressure, and the relatively high pressure of the water around them make the bubbles implode on themselves. And it may not seem that destructive because they're so tiny, but the resulting force is so large that this can collapse and take chunks out of metal. So one really cool example is when you look at marine propellers that have been in service for like 30 years, you see all these divots of metal just taken out. That's because of cavitation. Now, for most aerodynamic objects, cavitation isn't that likely to form because to get cavitation, you need to really drop the local water pressure. Here, for this it's called a barred owl wing replica, it is very unlikely that cavitation will occur here. So just quickly, if you wanted to learn OpenFoam, check out our course and link below. And now onto the second thing that you need to watch out for is wave generation in water channels. So if you submerge an object, but it is too close to the surface, waves will form. And this is additional drag, and this component of drag can be huge. So some studies on various bodies say that wave drag in this situation can account for well over half the total drag, like 60, 70, even 80%. So the creation of these waves also messes with the object's flow physics. So if you are to test an air-based object in a water channel, you want to make sure you submerge it enough so that the waves on top that are forming are negligible. So the depth changes from object to object, which you need to submerge it at, but for a streamlined object, generally like 3 thicknesses underwater is enough to cut out most of the wave drag, and by like 6 thicknesses under the surface, there's almost no wave drag. And I think for like humans, like, if you were to dive into a pool, you need to be like maybe 4 or 5 like body widths down under the water to start minimizing the wave drag. So as long as you watch out for those two considerations, you're fine to test air-based objects in water and vice versa. You of course need to match the Reynolds numbers and take into account blockage ratios, and the same you would do for a wind tunnel. And different objects might need different non-dimensional matching. So for example, reduced frequencies might need to be matched, or shrill numbers and so on. But now for their PRV setups, in my experience, they are much easier in water channels than wind tunnels. And that is because it is much easier to seed a flow in a water channel than a wind tunnel. So for PRV, you need seeding particles, which then reflect the light so you can actually see what's happening. And in water, particles will take longer to fall out of the flow than in air. So you're not as limited to what you can use. Now on the extreme end, you can literally use anything, but that doesn't mean that it's accurate to do so. But just to give you an idea of what you can use, when I was actually first learning PRV, I learned in a water channel first actually. And the water channel I was using had like a 30-year-old pump, and the insides of the pump were rusting and needed to be replaced. But for good investigations, for general investigations, it was still fine just to learn about what's going on generally and for learning purposes as well. And as we were learning how to do PRV, we noticed that these little bits of rust, these little brown specks in the water, were forming, and that were the rust fragments coming out of the pump, just being pumped out with the rest of the water as the pump was slowly eroding itself. And they were all of a similar general size, and we wondered if you could use these particles as seeding particles. So we ran some PRV, and the specks of rust were phenomenally good at reflecting light, even better than the particles that we were supposed to be using. So in terms of reflecting the light, you can use particles you never thought you could. Now in terms of how well these particles follow the flow, that is a different story. I need to size these particles properly. But in terms of just reflection, so many different particles you can use. Now, one downside of water channels is that any vibrations in the system, like from a pump, a rusted pump that's getting less and less accurate, for example, these vibrations get transmitted through the water much better than in air, so the vibrations of the entire system will corrupt the results. So that's something to watch out for in water compared to air. Now, for this experiment, the Reynolds number that they tested the Wing at was at 49,000. And the light sheet was 1 millimeter thick, which is okay. And that is actually another benefit of running PRV in a water channel. So with PRV, the main thing limiting the Reynolds number you can run the flow at is the laser sheet thickness. So on the one hand, you want to have the sheet as thin as possible, so you only measure the movement in two directions, the two lateral directions, the orthogonal ones to the free stream. Having movement in the third direction can corrupt the results. On the other hand, the thinner the sheet is, the less time the particles spend in the laser sheet, and you don't get enough information to run your PRV properly. So you have to drop the velocity so the particles stay in their flow in the laser sheet long enough. So for example, if you were to run your PRV and you were to take 2 snapshots in time, and between the first and second snapshot, 40% of the particles from the first snapshot have now left the laser sheet and are no longer visible. That means in the second snapshot, you only have 60% of the particles you had in the other one, plus 40% of other ones that didn't appear in the first snapshot. You can't really get good PRV measurements there because you can't actually trace where the particles go because half the flow is pretty much gone. As such, in a water channel, you can drop the velocity but still get the same Reynolds number, hence you can run the PRV with a thinner sheet but still have most of the particles visible in both snapshots and get higher quality results. So that is another major benefit of having PRV in a water channel as opposed to a wind tunnel. Now for this experiment, their frequency of the cameras was 1 Hz, which is very slow, but adequate for a general analysis. They also effectively averaged the results over hundreds of snapshots to get a general consensus, so just a time average kind of thing. Now, their cameras had a resolution of 29 megapixels, which is really good, particularly for PRV cameras. Usually PRV cameras are like 1-2 megapixels maybe, so 29 is very high. And that's actually probably why they have such a low frequency, because the amount of information the processor can handle isn't enough to allow a faster snapshot speed because the megapixels are so high. Just like when you take one snapshot, there's so much information going through the camera that it needs to process this before you can take another snapshot. So the uncertainty in the mean velocities was 1.25% and between 6 and 10% for the mean velocity gradients. So I guess the accelerations. So these wings were tested at 6 degrees, 12 degrees, and 20 degrees. And I'd be really interested to see what happens actually at 20 degrees, because most of our wings, like that we make, humans make, already stalled by then. So I wonder what our wings would do. As shown in figure 3, they also took the PIV measurements at 5 different planes over the wing from the wing root, so P1 here, to 25% span, 50% span, 75% span, and 95% span, which is almost at the wing tip, P5 here. One final thing to note is that their owl wing replica had a smooth surface, while in real life, the owl wing had a rough, velvety texture. So I'm a little surprised that their 3D printed replica is smooth, because pretty much all 3D printing will leave a surface roughness to some extent. So I don't know if they treated their surface, for example, maybe an acetone quick bath with smooth ABS, if they used ABS. I don't know what they did though here. They said that it's just smooth. Maybe they sanded it, looked perhaps. But it's a bit strange that the 3D printing was smooth and our wing wasn't. Maybe it would have been better to leave the 3D print rougher. Anyway, they say that this difference in smoothness will affect how the turbulent boundary layer is, and they say that in real life, the flow over the owl wing will be a little more turbulent than over their replicas. Now let's move on to the results. In addition to taking PIV planes across the wingspan, they also divided their data up along the chord from the R1, R2, and R3 zones. In figure 3 we see these, and this is based on the different zones. So R1 refers to the leading edge section. R2 refers to where the authors say that at high angles of attack, the flow may separate in this region, in R2 region. Then R3 is where the flow may reattach this region. Then in the trailing edge part, so past 80% of the chord, the last 20% of the chord, they didn't have any PIV here because the trailing edge was too reflective to get good results. So in figure 4, we see the boundary layer profiles in region R3 across the wingspan. The authors didn't put in the boundary layer profiles for regions R1 and R2 because they said that the serrations had minimal impact for these two regions. Now that right there already tells us one major feature of serrations. So in region 3, R3, where we see in figure 4, the serrations definitely have an effect across the boundary layers across all angles of attack tested. So let me zoom in a little bit, for example, here. So we see the serrations are always the dashed lines and the smooth ones are always the solid lines. So we see that the serrations always had such a massive effect on the boundary layer profile. So if the serrations had no effect on the boundary layer profile in R1 and R2 regions, then either the serration effects were too small to measure and they had to grow before we could see a significant effect, or the serrations affected other quantities in the boundary layer and these effects then had an effect on the boundary layer profile more downstream. Either way, with the typical way of measuring the effects on a boundary layer, the serrations effects are only noticeable well downstream of them, like 50% of the chord downstream and even more. Now let's go through figure 4 more because there are some interesting findings. And first of all, I just want to say that I'm not quite sure if I'm reading these graphs correctly. I say that because the y-axis is labeled y on c. So the distance above the surface divided by the chord is a non-dimensional value. That's how I'm interpreting this axis. Now, if that is what it is, then I'm a little confused because for some of these boundary layer profiles, their thicknesses are like 30% of the chord, which is massive. I mean, that's like having a couple centimeter thick boundary layer for a very small wing. It is really unexpected to me to have such a large boundary layer, but I can't really see any other way of interpreting these graphs. So I guess that's what it means. Anyway, the first obvious effect these serrations have on the boundary layer thickness is that they make it much thinner. You can see across all the different angles of attack for all the different locations, as I scroll across here, the serrations make the boundary layer profile much thinner. The serrations more than half the boundary layer thickness in some cases, like for example in P2 at 6 degrees, so the red lines, you can see here it's more than halved the boundary layer thickness. And so these serrations are effectively making the flow over the wing faster. I wonder if that also increases the lift production as well. Unfortunately, they don't give that information in this paper, but it'll be something interesting to find. Now, another major effect these serrations have is that they make the boundary layer profile far more similar across the angle of attack range. So you can see that where there aren't any serrations, so the solid lines, increasing the angle of attack regardless of the span-wise location, whether that's from P1, P2, P5, all the time, increasing the angle of attack pretty much results in the boundary layer getting thicker and pretty much doubles in the thickness from 6 degrees to 12 degrees, the red line to the blue line. But when you put the leading edge serrations on, the boundary layer thickness is almost constant across the angle attack range. So they have this very strong normalizing effect. Another very interesting thing is that these serrations, if you look at the maximum velocity throughout these boundary layer profiles, you'll see that the serrations make the flow in the boundary layer hit higher values than the free stream flow. So you can see here it's above 1, the normalized velocity. That means that it's higher than the free stream flow at the peak of the boundary layer, I guess. I mean, the boundary layer ends at 99% of the free stream velocity. So I'm not sure how you interpret this, but I guess you could say just above the boundary layer, the velocity is much higher, and then as you go higher again, it then drops. So literally just before the boundary layer ends, we get very fast moving flow, and just above that as well. That's insane and very rare. That makes me think that these serrations also allow the hour wing to pitch at high angles of attack, because if you have fast moving flow around the boundary layer, there's a good chance that that will help prevent the lower regions as well from stalling. So as the angle of attack increases as well, the maximum velocity increases as well. So the higher angle of attack is, the more effective these serrations become. That seems logical to me and something that evolution would do, because a higher angle of attack means that that would be beneficial for the owl for some extent, and that would then propagate forward in different generations. So unfortunately, they don't give any flow vis here, so I don't know the exact mechanism at play, but if I were to guess, I would think that some kind of micro vortices are being formed by these leading edge serrations, and as angle attack increases, the vortices become stronger and stronger. So that's what I think was happening with these boundary layer profiles. If you have any other ideas, let me know in the comments below. Let's move on to figure 5 now, because in figure 5, we see effectively the momentum loss. The values here have been normalized to the non-serrated airfoils on the y-axis here, where 1 means that there's no change in the momentum loss. A lower value than 1 means it's a less momentum loss. A higher value means a greater momentum loss. Now, this momentum loss can also be interpreted as friction drag. So more momentum loss means greater friction drag, so above 1. So it is immediately obvious that for most locations over the serrated airfoil, the momentum loss is less. The only real outliers are at 6 degrees, where the serrated airfoils increased the momentum loss in quite a few locations, so a few of these red triangles. For 12 degrees and 20 degrees, the momentum loss is reduced by up to 90% in some locations, like down here, 90%. That's pretty sweet. In fact, generally the serrated edge seems to have the greatest effect over the trailing edge, with the minimum momentum loss seen at the trailing edge compared to anywhere else. So again, the effects of the serrated edges are much more prominent further downstream towards the trailing edge. The momentum loss becomes less as opposed to near the leading edge. And overall, it seems like these serrations are reducing the friction drag of the airfoil. Now in figure 6, we see the ratio of the peak span-wise vorticity over the serrated leading edge compared to the smooth leading edge. And again, it's normalized with 1 meaning there's no difference. And as I suspected about how these serrations work, at least in part, the vorticity is definitely greater with the serrations than without. And only for a select few locations is the peak mean vorticity lower. So I think that we can conclude that the serrations are increasing the vorticity in the flow, and that is at least one mechanism that I think is resulting in the boundary layer profile being sharper, smaller, and having a higher velocity outside the boundary layer profile than in the free stream flow. So in figure 7, we see the effects of the maximum Reynolds stress in the streamwise normal direction. So for the CFDers out there, you will definitely recognize this term, Reynolds stress, because it is the main thing in RANs and URANs, and similarly, really the bane of these CFD approaches. Now, calculating the Reynolds stress like this would come in real handy if you were to look at the accuracy of RANs or URAN simulations. You could literally use these measurements to better refine the terminus model you were using. So you would run your CFD, check your Reynolds stresses and see if they are matching these, and then you could tweak your terminus model to get a much better result. This is actually very useful information if you use it right, and it's very rare to get this. Anyway, overall, for 6 degrees and 12 degrees, these serrations increase the Reynolds stresses, while at 20 degrees, they almost universally reduce them. So there's this dichotomy here in the flow physics, and either the smooth wing is changing between 12 and 20 degrees, or the serrated one is, or maybe both. Either way, the fact that the serrations are changing those Reynolds stresses makes me think that it might make it harder to CFD these flow control devices with RANs and URANs approaches. You really need a good terminus model to accurately handle this, which the Reynolds stresses here would help you do. So you'd need to just put a bit more effort in, but you got the information here to do that. Now in figure 8, we come across a fairly exotic quantity, the enstrophy. And the entropy is effectively a measure, it's a aerodynamic specific, or I guess fluid mechanics specific quantity. And it's effectively a measure of how quickly the energy in the flow is being dissipated due to viscosity. So effectively the stopping force acting on the flow. And this is directly related to the energy cascade, where big vortices continually break down into little ones until viscosity makes it impossible for any vortices to form. So in figure 8, we see that similar to figure 7, there is this dichotomy where from 6 degrees to 12 degrees, the entropy of the serrated airfoil is much higher across the span and chord. But for 20 degrees, the entropy is much lower. So the energy in the vortices aren't being dissipated as quickly by the viscosity. And I think that perhaps that's because as you go to high angles of attack, I think the vortices being produced by the leading edge serrations should be stronger. That's what I think. Anyway, to look at how the different flow physics, which they don't really present in this paper, contain different amounts of energy, they did something called proper orthogonal decomposition, or POD for short. So this effectively is looking at the periodic fluctuations in the flow and then breaking them down into their mode and classifying how much energy each mode has. In general, for aerodynamics, the lower modes usually have the most energy, and as you get to higher modes, you won't see much, and that also is the case for flow vis. Much of the higher modes is imperceptible because the lower modes are dominating the flow physics. So for example, in a cylinder, for example, the von Karman street is definitely the dominating mode, and it's usually like a lower mode. So in figure 9, they are showing how much energy the modes are containing with and without the leading edge serrations. And overall, for both types of wings, as expected, they contain most of their energy in the lower 4 or 5 modes, like 80 to 85%. But above that, there is still some energy, but honestly, I don't think much can be concluded from this graph because we don't have the flow vis to help. Even in figure 10, which shows some snapshots of the flow vis, they're kind of just showing bubbles and a few vortices, but I don't get enough information to get a good idea. But anyway, at least we can see that the lower energy modes contain most of the energy. And with that, we come to the end of this podcast. So we saw that these relatively tiny serrations have a very large effect on many different properties. I was quite surprised at just how much they affected the boundary layer, and it looks like the underlying mechanism for them, at least in my opinion, is the creation of vortices that permeate through the flow, and as the angle of attack gets higher, I think the vortices get stronger. We also saw that there is potential for these serrations to make the wing less susceptible to flow separation, as well as likely reducing the friction drag, which is impressive, because usually a greater robustness to separation comes at a cost of higher friction drag, because to resist flow separation, you need a higher velocity in the boundary layer region, and that results in a higher friction drag, but we don't get that here. So this is very clever. And finally, if you want to learn how to do OpenFOAM, check out our links below. And if you're doing experiments and you did you know that there is likely a 2 to 4% error in your experimental data and you don't even know it? In the Atmosphere Hawk link below, we go through the math as to why and how to correct it. So if you like this podcast, hit the like button and the subscribe or follow button, whichever platform you're on. And we'll see you next one. Peace, amigos.